Let us now understand why the KMP algorithm works in linear time. Recall that the computation of the failure function takes time big O of m in the worst case. As the size of the input is n plus m, this call is at most linear in the size of the input. So far so good. The running time of the rest of the computation is dominated by the while loop. Each iteration of the loop takes constant time. To obtain the running time of the entire loop, we just have to count the number of iterations. We will count the number of iterations using a visual method, by analyzing the positions of the indices I and k relative to the first item in the text. We call these the screen positions of the indices. The screen position of I is exactly the value of I. The index k points to an element into the pattern, and therefore its screen position consists of two components, the value of the index I and the value of k. Let us analyze what happens to the screen position of the two indices in each of the three cases of the conditional statement. In the first case, the current comparison succeeds. The screen position of the index k increases by 1, and we use an arrow pointing up to recall this fact. The screen position of I does not change, and we use an arrow pointing left to recall this fact. In the second case, the comparison fails when k is 0. The screen position of each index increases by 1 unit. We recall this by two arrows pointing up. Let us move to the third case, which occurs when k is strictly greater than 0 and a comparison fails. Consider the longest proper border of the current overlap and call its length L. As L is the length of a proper border of a string of size k, the value L must be strictly less than k. Concentrate on the screen position of the index I. It conceptually moves by k units to the right and then by L units to the left. As L is strictly less than k, the screen position of I increases strictly. We recall this by an arrow pointing up. The index k gets reset to the length of the current border and therefore its screen position does not change. We recall this using an arrow pointing left. To summarize, independently of which of the three cases we enter, the screen position of at least one of the two indices increases strictly, and the screen position of the other index does not decrease. The screen position of I can only go as far as n minus m, because after this position there are no more valid offsets. The screen position of index k can only take n steps to the right before the pattern reaches an invalid offset. So there are at most n minus m plus n iterations of the while loop, which is big O of n plus m. It follows that the running time of the algorithm in the worst case is big O of n plus m, which is linear in the size of the input. In the follow-up tutorial, I will show how the truly understanding algorithms presentation of KMP that we have just seen relates to the more standard treatment that you might find in many algorithms books, just in case you need it for your class. Subscribe to the Truly Understanding Algorithms YouTube channel and hit the bell icon so that you get notified when the next upload goes live.